Okay. And let me look at the people here. So it still says John or pardon me, Don is still joining. Um, there he goes. So he's an official participant. Okay. And as I was telling Lucy, at the right side of your screen, you probably have you should have two arrows here in this little purple tab. And if you poke the arrow out, well, I guess one other thing, you see your audio should be here and it might be muted. Um, and I guess I can also see if you click on this, that'll raise your hand. But planning to just monitor the chat while we were going on. If you click on this little bubble, once you expand that pane, you should see the chats, things in the chat window. I'm not sure. I think people who've joined late might not see previous chats. So in your own chat window, you might not see this stuff. You'll only see it on my screen, which should be showing up on your screen. So I hope that Lucy and Don will complain if they can't see something or are unable to chat. I don't know. Maybe they'll send Jessica an email saying, help. Okay, so I'm just going to talk for a while about the sun, which to most people is kind of a boring yellow ball up in the sky, but it's actually pretty interesting if you study it in a bit more detail. This is not actually a picture of the sun. This is a picture of the moon, which is blocking the sun in an eclipse. And in the background, you can see these white, wispy structures. They're related to the sun's magnetic field. And what we're actually seeing out there are some density enhancements in the solar wind. And maybe you can see some little bright pink things here. That's emission from the low solar atmosphere. So this is one of my favorite eclipse pictures. It's been heavily doctored to kind of show edges and contrast more clearly. So if you took it with just took a picture of an eclipse with a normal camera, it wouldn't look this quite this spectacular. But okay, so let's see. Here's an abstract. I'm not going to have us read the abstract, but I just include them in all my talks. I can send somebody a copy of my slides if they're interested. And I'm making a recording of this too, so I can furnish Jessica with a recording of the talk if she wants it. They'll come out, an hour of talking will come out at about 400 megabytes. But it can be uploaded to YouTube and stuff like that. So I'll just talk about, this idea of I tell you what I'm going to tell you, and then I tell you, and then I tell you what I told you. So I think one of the main ideas I want to get across is that the sun is, as we would say, an active star. So it has all kinds of manifestations of what we call solar activity. So there are things like, it's not just a blank white ball, there are sunspots, and then we'll talk about active regions and elements or prominences, and then we'll talk about solar flares and coronal mass ejections. There are all these manifestations of solar variability. So it's not always just the same sun. But all of these things that I've listed above here, they're all ultimately powered by the sun's magnetic field. So the magnetic field is really the thing that changes on the sun, and it causes all these kinds of phenomena. We'll see pictures of all these in a few minutes. And then it's important practically to study solar activity because the Earth is bathed, if you will, in the solar wind, and magnetic disturbances that propagate from the sun, streams of high-speed particles that propagate from the sun to the Earth can disturb what we call space weather, the near-Earth space environment. And so this has consequences for the satellites, can damage satellites or disable them, and can hamper radio communications, and can cause problems with power grids, and can be dangerous to astronauts. So there's a whole lot of what we call space weather impacts from solar activity. And as we think about going to Mars and stuff and other planets, sending humans out there, we have to deal with solar activity, not just at Earth, but in the whole inner heliosphere, we call it. Let's see. So I guess I thought I had run this, but let me do this. It's going to say select. I'm going to grant access. It wants to run a movie. This is a picture of a sunspot. It's a movie taken by a joint NASA, Japanese, UK satellite. And so the sunspot itself, and I think I probably have a couple little for the oops, and this is wrong. I think I resized my screen and I pointed the arrows got pointed at different places. The umbra here, let me, you'll see how the sausage is being made here. The umbra, oh, okay, so it's in the right place when I view it here, but I must be in the wrong aspect ratio when I'm showing my talk. So let me just resume that. The umbra is this dark region, and the penumbra is the neighboring area around the dark region. And so this whole thing we would call a sunspot. And these have been observed back a couple thousand years. You can't look at the sun with your naked eye, but on cloudy days and hazy days, people were able to see that there were blemishes on the surface of the sun. And in the background, you can see all these this kind of flickering and all these little motions. This is called convection. It's kind of overturning and churning of the gases that make up the body of the sun, that has variations in their brightness. So we call that granulation is the structure here, the modeled structure we see, and then those two things are going to show up. And people have been drawing pictures of sunspots for a long time, even before we had cameras and telescopes to observe them. And this is something from the 12th century. And so the historians think this is an umbra, and this is a penumbra around each of these. So we knew that sunspots were there a long time, and Galileo had the first telescopic observations in the 1600s, but they seemed to be kind of random, or nobody had noticed a pattern until 1843, when Schwabe, a German, I think he was a pharmacist, decided to make a plot of sunspot time, and he noticed that there was a cycle, a recurring pattern, that they came and went with an electric cycle. Now, Schwabe was making his plots here just a little before 1850, and back in from around the time of Galileo on through most of the 1700s, there was something we now call the Maunder minimum, where there was, for still unknown reason, very few sunspots. And so I think if there had been regular sunspot cycles during this period, we probably would have noticed that there was a pattern sooner, but it took a few cycles after this minimum ended and sunspots returned for them to be seen. And I should probably see if there's a more recent one of these. I think we've gone down all the way and we started heading back in the next cycle. It's interesting to note, though, that even before this plot was made, somebody had a thought that, well, we've seen all these, as this person puts it, movements of heavenly bodies like planets going around in regular orbits. Somebody thought, well, just based on this principle, it seems like everything in nature goes through cycles. We're probably going to find cycles for sunspots too. So he made this claim way back in right around here. So there actually had been a couple of peaks in blue here. Oopsie, put that back. I want to focus our attention here on this top plot for a while. If you just kind of relax your eyes and forget about the jaggedy ups and downs for a second, and maybe you just kind of try to lay a ruler or fit something, a straight line to the tops of these peaks, you might have thought that there was an upward trend, that the peaks more recently are bigger than the peaks from a long time ago, and there were no peaks down here. So there was a thought that maybe there was a general increasing trend in the numbers of sunspots, and that's what I should say here, is that we're plotting the numbers of sunspots. We're not plotting how strong the sunspots are or anything like that, just their number frequencies. How often do we see them? And so there was this thought there was a general trend, and this had implications for our climate. Maybe there was increasing energy coming from the sun, but people have gone back and done a more careful job of looking at the records, and they think that there is no real trend here. That what they think was that there was a systematic bias, that the way people were recording things back here was different than the way they were recording them more recently. So you have a choice. You can downgrade the current things or upgrade the old things. But anyway, you get kind of a flatter profile of sunspot occurrences. And so I think I have this quote here: the scaling difference between the older stuff down here and the new stuff was differences in telescope aperture. We have bigger telescopes now that are better able to see smaller sunspots. And then there were these two Swiss people who were involved in counting these sunspots for a chunk of the late 1700s and 1800s, I believe, Wolf and Wolfer. And it turns out Wolf, I believe it was, counted things very differently than kind of, I would say, normal people would. So there were some, they had to work out some calibrations. Fortunately, both of them and their assistants kept hand drawings of sunspot maps. So you can kind of go back and look at the maps and figure out how they were counting things and relate our present systems with those older systems. So I'll put that back. And then I should talk about how sunspot cycles work. This is a plot of time, and here this is solar latitude. So this is the sun's north pole and the sun's south pole. And what happens is they put a dot at every place when there are some sunspots, and then there are a whole lot of sunspots in one place. The dot gets, it first starts black, and then the color gets red, and then gets yellow. So it kind of gets brighter. So there were a lot of sunspots right here, stuff like that. If you make these plots, you see that in time, the sunspots start at high latitudes and then move down to low latitudes. And these look like, basically like butterfly wings, so people call this a butterfly diagram. And so this is one particular systematic aspect of the pattern of sunspots, their emergences, because we believe they emerge from the interior of the sun. And so, example of a sunspot seen in white light when we have the whole disk of the sun. So this is what you would get if you took a camera, or maybe you have you have a telescope of your own, and you put what we would call a neutral index filter, just a kind of a dark glass or plastic filter that blocks most light. And you need to buy something that'll specifically block UV light too if you look at it. But if you recorded an image, you would just see kind of a gray sun because you've blocked out all the colors essentially. And then you'd have some spots on it. And these have actually been given numbers. I'll talk a little bit more about those numbers in a minute. And then as I mentioned, we're now aware that the sun influences the Earth's space weather, and we understand in a lot of ways how, because we know about magnetic fields now, and we know about protons and electrons, and atoms and stuff in the solar wind. But there was a time when we didn't understand these things very well, and so this was right around the time shortly after Schwabe figured out that there was a cycle. These observers independently noted that there were changes in the Earth's magnetic field, how compasses varied slightly, and how there are what we now know are magnetic storms, which are related to the northern lights, the aurora borealis. That kind of magnetic activity was in sync with these sunspot cycles. So that was in 1852, just a decade after Schwabe did that. And then in the late 1850s, Carrington saw a solar flare, and so he was making sunspot drawings, and you can see he's got the sun's longitude and latitude here. And I see we got a couple more people joining. And he drew these little brightenings that he had seen. He had this projected onto a table in his lab, a telescope, magnified an image of the sun, and then shone the light down onto a table. And he would lay out a piece of paper, and he would trace things on the table. And he saw these two intense brightenings, and with time he saw them move. So the brightenings he first noticed were at A and B, and then this one kind of moved over to point C, and this one moved over to point D right at the end. And then just a couple days later, there were some magnetic variations that they measured, and Carrington was in the UK, and they measured some magnetic variations there, and we saw auroras all over the world, even as far south as Cuba. So this was a really big magnetic storm, and for a flare to be seen with a naked eye like this, without a telescope to really help gather light. He did have a telescope, but it wasn't a very powerful one. Meant it was a very powerful flare. There are many flares that can't easily be observed without detectors. And I mentioned these bright features. And then for scale, I just wanted to show you how big the Earth is. This little dot here is the Earth. And yeah, I think you can see this is 10 solar degrees in longitude. And so a good sized sunspot will be, the umbra of that sunspot will be several times as big as the Earth. And these flares, take up a volume that's bigger than the Earth, bigger than a few Earths. So I'm going to focus on basically three aspects of solar activity. I want to talk about the fact that the solar atmosphere is very hot, hotter than the surface of the sun. I'll talk a bit more about that, and I will probably occasionally use Kelvin to refer to temperatures, but you guys might know about Kelvin. But if you don't, 1 Kelvin is the same thing as 1 degree centigrade, or 1 degree Celsius. So we want to understand why the sun's outer atmosphere, part of its outer atmosphere is the chromosphere and the corona, why those are so hot. And we would like to know why sunspots come and go. And we'd like to understand what causes solar flares and some things that I'll talk about in a while, coronal mass ejections, or CMEs. As I mentioned earlier, all the kind of manifestations of solar activity or solar variability that we observe are related to magnetic fields, and we think that this activity comes from convection in the sun and then and movement about the sun. So I want to talk about what the sun looks like within, inside, and then its outer atmosphere. And I need to talk a bit about plasmas. The sun is a very hot gas, and so it's called a plasma. And I want to talk about what that is. So here's a cutaway picture of the sun, and I showed a movie earlier that had this kind of modeling on the surface. These little bright crinkles, if you will, or something. Those are that's granulation. I think I probably set things up to kind of scroll through things here, so I'm going to click through a few things. But all of the layers of the sun are gas in one way or another. And I need to remind us, as you probably know, or I hope you know, that heat can flow in three ways. You can have conduction, that's when things touch each other. Radiation, that comes from photons or from light. Maybe it's not visible light, could be X-rays and radio waves, things in wavelengths we can't perceive with our eyes, but nonetheless it's light. And then convection. And convection is what we're familiar with when we think of heat rising. Smoke rises from a campfire, or on a hot day, the sun warms air and that rises up and forms, thunderstorms and stuff like that. That's convection. Because what's going on here is in the center of the sun, in the core, there's heat being produced by fusion, nuclear fusion. Hydrogen atoms, which have 1 proton, are fused in a series of reactions to make helium, which has 2 protons and 2 neutrons. And this is what really produces all the sun's heat. But then that heat needs to migrate out from the sun. And as it does, different modes of heat transfer occur. So in the radiation zone, or the radiative zone, the heat that was created in the core moves outwards, and that's the dominant heat mechanism. At some point, though, the density falls down low enough, and radiation can't move heat fast enough, so then the gas itself begins to move. And this is what happens when when smoke is rising from your campfire, there's hot gas near the campfire, and the gas itself moves and carries the products of combustion, that smoke, with it. And eventually, basically the density of the sun drops off low enough that light, particles of light, photons, can escape. Below the visible surface of the sun, the gas is so dense that photons tend to bounce off other gas atoms before they escape. So we can't see down into those layers because what our eyes perceive are these photons. So in order to see an object, there needs to be a clear path for the photons to move from the object to us, and there's no clear path once you're below the photosphere. So photo shine or photo light, the root here, the linguistic root, this is the part of the sun that we see. So it's the visible surface of the sun. To be clear, it's not hard. There's nothing you can bang on with a hammer. It's just gas. But it's and it's that escape of those photons that enables us to see it. Just above the photosphere, there's the chromosphere, and it's hotter than the surface. The surface is about 6,000 degrees centigrade. The chromosphere is about 10,000, and again, I'll lapse into using Kelvin here. So it's substantially hotter. And then the outer atmosphere, which we can't perceive generally because it's so thin, there's hardly any visible gas there. We need special observing techniques to see it, is actually about 1,000,000 degrees centigrade, or about 2 million Fahrenheit. So this is what's going on. And when I talk about that, this previous slide here, that's for a chunk of the atmosphere, the chunk of the sun's atmosphere is hotter than the surface. And so what I've shown here is a plot of the temperature of the sun as you go from the core out to the surface. And this behaves like we're kind of used to. You have some source of heat, that's the fusion in the core, and as you move away from the source of heat, it gets colder. And this is how our campfires work. But once you get outside of the surface, and this is from the surface up, so this is going in kilometers, and this is 100 kilometers above the surface. Now we're 1,000, and somewhere this is about 2,000 kilometers above the surface. All of a sudden, it starts getting hotter, and then you go out to 10,000 and 100,000 kilometers above this. And the temperature is up here around this 10 to the 6th is 1,000,000 degrees. So this is a very hot gas. So this part is the change from kind of low temperatures up to high temperatures here is what we call the coronal heating problem. And ultimately the source of this heating basically has to be the magnetic field of the sun. And I'll talk more about those magnetic fields in a second. Before I do that, I want to talk about the kind of gas that the sun is. It's a special gas. We call it a plasma. You might have heard it called the fourth state of matter. The three states of matter we're kind of most familiar with here on Earth are solids and liquids and gases. And this is increasing temperature. If I take something and I heat it up, it'll melt from a solid into a liquid. And if I keep heating it, it'll eventually dissociate from the liquid and kind of evaporate to form a gas. We think of evaporate as like a vapor, but the idea is similar. Just the atoms or molecules that rise the liquid will all have space between them when you're a gas. But if you heat a gas even farther, remember, heat is the motion of particles. The particles will start moving around faster and faster until in their collisions, first they will break apart all the molecules, and so you'll only have individual atoms. And then they'll break apart the atoms themselves by knocking loose some electrons. And that's when we have a plasma. Plasma is a sea of negative charges, electrons that have been knocked loose from their host atoms, and then the positively charged atoms that have been left behind because they lost an electron, a negative electron. So I think this is just, these bullets probably say what I just said, so I won't dwell on them. But temperature is related to the speed of particles. And so here they show this is another representation of a gas versus a plasma. In a gas, you have electrons orbiting their nuclei of the atoms, but in a plasma, the electrons get knocked free. And this would be a good example of a hydrogen plasma, where the nucleus is just one proton and there's just one electron. And then this is, I would say, a completely ionized. I've taken every possible electron off of its host atom or host nucleus. Sometimes you get plasmas that are partially ionized, where only some of the electrons have been stripped off. You might not have known this, but of the matter that we can see, so I'm not talking about dark matter, plasma is actually the most common thing in the universe. And if you think about it, it does make some sense that a lot of what we see is stars, and stars are hot, so they're all plasma. And then we see a lot of hot gas clouds between the stars, and those are hot enough to be plasma as well. So there's, as far as most of what the universe is made up of, it's stars, and then it's the gas clouds of which the stars were formed. And then when you do have these separated charges, positive charges and negative charges, or positive ions and negative electrons, you get some strange behavior. So I need to talk about that for a second. I think this is a German slide, so they have electron here with a K in it. But what they've shown is some magnetic field lines here. And the way you should think about a magnetic field line is just, you can kind of think of it as a string that goes from one place to another. There's a place where the magnetic field starts, and there's a place where it ends. I guess to be precise, I should say that they always form closed loops. But from our point of view, we want to think about magnetic fields, starting from someplace in the sun, leaving the sun, then going back into the sun somewhere else. And when there are these magnetic fields, if there's a charged particle, they can't move across the field. If they try to move perpendicular to the magnetic field, they end up swinging around the magnetic field in spiral shapes. So they trace out kind of these helical motions that kind of look like slinkies. And the diameter of the slinky depends a little bit on the speed of the particle and stuff like that, and the strength of the magnetic field. We're not going to worry about that. But they can move along the magnetic field, but they can't move across it. So they can the way I think about it is like a bead on a string. It can move along the string, but it can't move across the string. And I think this just says that. So the particles are kind of trapped on their strings. And there's funny pieces of information that observations that can be explained by this. One is that comets have we can observe two tails. One of the tails is often curved, and it's the dust that gets left behind by the melting comet as it moves around the sun in its orbit. And the other tail is what we call it is an ion tail, and it points along the magnetic field out in space. So you can kind of see the two tails there, and I forget which is which. I think the whitish one might be the dust tail, and the bluish one might be the ion tail. And it probably doesn't say that here, but and this also explains an interesting fact that we here on Earth are protected by the magnetic field of the Earth, because the particles in the solar wind, and there are a lot of protons which have a positive charge and electrons out there which have a negative charge, and they move very quickly away from the sun. But when they come to Earth, they can't move through our magnetic field to hit us. Instead, they get deflected and bent around. And now sometimes they'll hit our atmosphere, our upper atmosphere around the poles. And when that is intense enough, when the stream of particles when there are many particles, that can cause the northern lights. But some of the particles actually just go around the Earth. The situation on Mars is very different. It doesn't have a strong magnetic field like Earth does. It has a very weak one, and that basically stripped away between the solar winds, particles. Mars' atmosphere basically stripped away Mars's atmosphere. So if we did not have a magnetic field, our planet probably would not have a very dense atmosphere, and life might not be sustainable. We might all also have cancer because all those particles, the incoming radiation, would mutate our DNA. So we're very happy that the Earth has a strong magnetic field to protect us and our atmosphere. Because these charged particles move like beads on a string, we say that the magnetic field is frozen in, or that it moves along with the plasma. And so if I just had something that was infinitely conductive, a very good conductor, like better than copper, then magnetic fields can't move through that material. And so if I have a conducting ceramic, you might have seen images of a superconductor, it'll float above a magnet. But space is a pretty darn good conductor. It's nearly a vacuum, and so there's no obstacle to charges flowing. So an electron can just keep on going forever, or the same thing with a proton. So this is a pretty good conductor. And so in things like in stars and accretion disks around black holes where matter is falling into the black hole, the magnetic fields that are present there are, we would say, frozen in. So as the star rotates, or as the accretion disk rotates, the magnetic fields rotate too. And this is getting a little technical. I don't really need to talk about that. But we know nowhere is the conductivity of something actually perfect, but it's way slower than the movement of magnetic fields tends to be way slower than the velocities involved. So this has consequences for things like the sun. If you have plasma or gas inside the sun moving at some velocity, it just drags the magnetic field with it. And I should talk about sunspots, and I'm talking about magnetic fields because sunspots are magnetic, and this was realized a bit over a century ago. This was an image from Hale, who is an observer at the Yerkes Observatory down around Chicago or southern Wisconsin. I believe it's at Lake Geneva. They took images of a sunspot, and they put a slit across it so that light came in from a slit, and they diffracted the light with a prism. So they made what's called a spectrograph, because it breaks light into its spectrum. And you can kind of see three little bands here. So this is a picture of the sun, this is a picture of the slit, and this is a picture of what they saw after on another plate, another photographic plate, where the light from the spectrum, the slit, excuse me, had been projected. And the fact that there are three kind of separate little bands here reflected the fact that the magnetic field in here was splitting up the spectrum. So there's the spectrograph slit, and there's something we call the Zeeman effect. When there is a magnetic field it'll split a spectral line. So Hale proved this proved that sunspots were magnetic. And as somebody put it kind of snarkily, astrophysicists are kind of obsessed with magnetic fields. It's now, anybody who's studying stars, or a lot of people are studying black hole atmospheres and stuff, and neutron stars, are really focusing on magnetic fields. So this is a key aspect of what astrophysics is these days, much as sex is to psychology. Now that we've got better kind of observational capabilities, we've learned that it's not just sunspots that are magnetic, but actually the whole kind of surface of the sun, the photosphere, all around them is magnetic. And so this is a magnetic field map on the right, and it was made with that Zeeman effect. The fact that the presence of a magnetic field alters a spectral line, we can work backwards to figure out what the magnetic field looks like. And so this is, in the solar context, a magnetogram is a 2D map of the magnetic field. And places here where the magnetic field is black, or where the field points away from you, and where it's white, it points toward you. And for those who know what these things mean, the peak strengths of these fields are about a third of a Tesla, or 3,000 Gauss. For reference, the Earth's magnetic field is about half a Gauss. So these are much stronger than the Earth's magnetic field, several thousand times stronger than the Earth's magnetic field. And then here's a movie, which I hope will work without asking me for permission. Oh, it wants to do this. I don't know why it's doing this. It might have been that I updated my operating system recently, or changed my password or something. So here's a movie over about a month. It's January 2005, showing maps of the sun's magnetic field, and you can see things. There was a sunspot just appearing, emerging from the interior. It'll come around again. There's something emerging, big old region emerging. And you can kind of see this dispersed salt and pepper pattern. And kind of all scales there are magnetic fields. And here's a picture of the Earth again down here. Pretty tiny, and I think I have that. So what we've learned now that we have the ability to kind of observe the sun and with finer spatial resolution and time resolution, that these magnetic fields are everywhere. And here's what we think is going on with these magnetic fields. We think there's processes we don't really understand create some magnetic fields in the solar interior. We have some models of how this works, but there's a lot of uncertainty in the models. And this magnetic field, because there is magnetic field in it, there's less gas in it, and so it becomes buoyant as a lower density, and so it rises up to the surface. That's what this red dashed line is. And then once it pokes through the surface, what we see at the photosphere is a sunspot if we look in white light, or if we have a magnetic field map, we can see that where the field comes out of the sun in one place and goes back into the sun in another. And then out in the solar, the sun's corona, we see the magnetic field going from one, what I'll call a foot point, to another foot point, a place where these magnetic fields are anchored. So this kind of structure that spans from the interior through the surface out into the outer atmosphere, then back down into the interior, we think this is what's going on. So I should say, yeah, the magnetic fields here in the interior, where the gas pressure is very high, confines the magnetic fields, but out in the outer atmosphere, in the corona, the magnetic fields expand and they fill all the space. So we can only see magnetic fields here, but that's just because these are the things that happen to be emitting. There's probably also magnetic field out here in these dark areas, and it's just not making bright lights. And I have this as an EUV image. It's extreme ultraviolet. So that's a wavelength of light our eyes can't see, but we have telescopes that can see with those wavelengths, and they show us stuff that's about 1,000,000 degrees. So this is these are dense loops that are about 1,000,000 degrees. We think the stuff out here is about 1,000,000 degrees too, but there's not enough stuff out there to emit for the camera to detect its emission. So there's all sorts of emission from the sun that is correlated. There are many sorts of emission from the sun that are correlated with the number of sunspots. And these are a few different plots of things. The blue line here is the number of sunspots. It goes up and down. I think these jagged lines are daily observations of how much radiation we get from the sun. The red line is an annual, it's kind of a smooth thing. The green line here is a radio flux. It goes up and down. The green line is the frequency of solar flares. The purple line is a radio flux that goes up and down with the sun's activity. So there's just all of these sorts of manifestations of energy being emitted by the sun, radio waves and flares, and the radiation we perceive at Earth vary with sunspots. Here's another image of this. These are X-ray images. The X-ray images, the bright regions here, correspond to regions that are a few million degrees hot. And as the solar cycle proceeds, this is a time with a lot of sunspots, and you see fewer and fewer brightenings in X-ray, and then you get down to here where there's no sunspots, and then there's a lot of sunspots again. Underneath each one of these bright regions, there is a sunspot. And let's see, I made this talk a few weeks ago before we canceled my original talk. So I should actually read this right now. But one thing I'm going to point out, because it might not work, when I go look at this website, solarmonitor.org, the sun might be boring, but here are basically three sunspot groups, or three active regions, I would say, in a magnetic field map, where you can see the black and white regions. And then over here, you can see out in X-rays, that's what's shown down here. You see 3 bright blobs. So these are kind of 3 smallish active regions. And these are 2 extreme ultraviolet images, and they also show brightenings. This is just supposed to be a white light image. It's kind of a bit false color, and this is with another wavelength of light. One key thing to keep in mind is that the sun looks very different in different wavelengths. In these images in the bottom, the surface of the sun looks dark because these telescopes are made to observe gases that are very, very hot, and the surface of the sun is not hot enough to appear bright to those telescopes. They only show things that are you know, 1,000,000 degrees or so or hotter. But yeah, let me call up a browser here. Well, maybe I can do it here. I'm going to pop a tab. I'm going to pull it over here. I'm going to go to solarmonitor.org. Oops, solarmonitor.org. And we'll see what we see for today. There's not much going on. Looks like there's a little sunspot group going down here. So there's a little sunspot group in the lower right quadrant. And one thing that's kind of funny when we talk about the sun, because it's up in the sky, if you think about it, if you look at it, the right side of the sun is to the west on Earth, and the left side of the sun is to the east. So we talk about the right side of the sun being the sun's west limb. And in the atmosphere above that active region, you can see some brightenings in this very hot gas. And so the coronal heating problem is to try to explain why these hot blobs are there. So you can go to solarmonitor.org yourself any day and see these things. And they'll talk about some flares. Let's see. This is talking about the types of active regions, and neither one has produced a flare, but these aren't very, these types of active regions don't generally produce a lot of flares. So I'm just going to minimize that for now. And so this is, again, something to show the relationship between magnetic fields, which are shown on the left with magnetic field maps, the black and white maps, where black is the magnetic field going away from you and white is the magnetic field coming towards you. So this is a time with a lot of sunspots, and the sunspots get fewer and fewer. So this is what we call solar maximum. We go down to solar minimum, where there's almost no magnetic fields on the disk of the sun, and then back up to solar maximum. And this is what the overlying atmosphere looks like. Lots of X-rays, very, very few X-rays, no X-rays. Well, there's some, but they're very weak. And then back to lots of X-rays. So it's really the magnetic fields that's driving that heating. And this, here's another plot. And this shows that, and this is a measure of how much magnetic fields there are. We call it magnetic flux, the measure of how much magnetic fields are present. And this plot on the horizontal axis, and on the vertical axis is how many X-rays are being emitted by regions with this much magnetic field. And it turns out, so here's the images of the sun here. Forget about this little knee thing. There are lots of other things on here. I should go back. These are other stars. So this kind of relationship, straight line relationship here between the sun and other stars, or between magnetic fields, I should say, and the presence of X-rays, which are given off by hot plasma, holds in lots of settings. Now, if I know right, this is the whole disk of the sun. I think these are probably active regions. These might be very small scale magnetic little clumps, and these might be individual pixels, but it's been a while since I've looked at this paper. So yeah, this is the coronal heating problem. Why is this hot atmosphere, this 1,000,000 degree stuff above the outer atmosphere of the sun? And kind of but one answer is that the sun's the motion in the interior, the convection that carries heat from the interior outwards, and this is kind of a big zoom of convection. So this is what the surface of the sun looks like with a high resolution telescope, and you can see these it kind of looks like bubbling lava or something like that, hot stuff bubbling up from the interior, and then the heat reaches the surface and it radiates out into space and it cools, and then the gas shrinks back down. That's what these dark regions in between the bright regions are where gas is sinking again. And the little arrows show our estimates of the velocities at the surface. We think that the velocities here, as this, we could call it overturning or this churning, put energy into the magnetic fields. And I just for jargon, I can tell you that these bright areas here, large bright areas, are called granules. And yeah, if I had a Texas graphic, I could put on top of here. One of these granules is about the size of Texas. And there's a lot of pixels here. Each one of these pixels is about 25 kilometers across. We can't quite, this, we would say it oversamples the sun. We can only see down to about 75 pixels clearly with this telescope. And so there's that convective motion stirs up electric currents, basically amps of electricity flowing in the sun atmosphere. And then if you dissipate those currents, you release heat. And so this is the how those things happen. And there are two models of that. One is this one on the right. I was kind of talking about shuffling of foot points or twisting or winding of fields around each other. And so this is a cartoon picture of how a field can wind around other fields. And this is somebody else looking at some Doppler signals, and they saw some kind of back and forth white black Doppler signals, which corresponds to positive negative Doppler motions or velocities. So they think that this is waves, and people call this AC heating. It's like alternating current. And this kind of winding people think might create steady currents that when dissipated would heat. So people talk about AC versus DC coronal heating models. We don't know which is right. We have a lot of models that claim to work, but we're still trying to figure out good observational constraints that can show us which one of these is important, most important. And one thing we still don't know is in detail, we can see that there probably are these currents based on the velocity patterns we see, and there probably are these waves, but we don't understand exactly how they're dissipated, and if that dissipation process that converts the electric energy in the currents or in the into heat. So that's the coronal heating problem. Now I want to talk about what we call the dynamo problem. What creates those sunspots? Where do they come from? Where do they go? Let's see. Oh, sorry, I went backwards. Excuse me. Hale noticed something on time ago, that on large scales the magnetic field is organized. And maybe if you stare at this, forget the white box. That's just where I grabbed this image from a long time ago. If you stare at things for a while, you might see some patterns. Excuse me. One thing I want to draw or I should point out to you is that the sun's north pole is the top and its south pole is at the bottom. So the equator runs across the middle. One thing you might see is that there's kind of a band of activity. The sunspots are pretty much at the same band, and that's related to what I showed you earlier with those diagrams, that solar cycle. Sunspots start at high latitudes. Their occurrence is at high latitudes, not low latitudes. And later on, when new sunspots emerge, they emerge at middle latitudes, and later on, they emerge at lower latitudes. And any sunspot over time, what happens is those convective motions shred the field. They disperse it. So it kind of gets smeared out. So this is a relatively young active region. This spread out stuff is an older active region. And then maybe you can see some fainter spread out stuff here. That's an even older active region. And so these magnetic fields disperse out over the surface of the sun. But in addition to those bands, another thing you might notice is that in the northern hemisphere, and the sun is rotating to the right, I should say, in the northern hemisphere, it goes, in the sense of rotation, the leading polarity is white and black, white, black, white, black, white, black. This is kind of messed up, kind of hard to tell, but it might violate that order. Sometimes these things violate that order. Here's white, black. But in the southern hemisphere, it goes black, white, black, white, black, white, black, white. So there's an ordering of things. So that's Hale's law. And maybe I have an infographic here. There's this mirror, or a text box here. There's a mirror symmetry. the leading polarities having the opposite sign in each hemisphere. There's also something called Joy's law. These tend to be tilted. They're kind of slanted a little bit, almost like chevrons or something, or they're tilted a little bit toward the equator. But a cartoony picture of what's going on is that when there are no sunspots, the sun's magnetic field roughly corresponds to that of a bar magnet. And the field looks very organized. And so in a bar magnet, you have a north pole and a south pole, and the magnetic field comes out of the north pole and goes down into the south pole. So we might call this side the positive end of the magnet, that's the negative end of the magnet. But that's arbitrary. So that's, if I make a plot of sunspot number, that's the solar minimum. And then at solar maximum, this magnetic field is no longer so organized, and it's kind of broken up. And I've drawn this bar magnet turned sideways, but that's kind of misleading. It's not like it all turns sideways. It's like the magnetic field inside gets scrambled. And there are many places where the magnetic field pokes out of the Earth as a positive region and goes back into the Earth as a negative region. So there's lots of little north and south poles, and each one of those basically corresponds to a sunspot. So that's a solar maximum. And then at solar minimum, again, the field is again organized, but it's flipped. Before, the North Pole was at the southern end of the sun, and now the North Pole, the magnetic north, is at the northern end of the sun. So the sun isn't flipping, just the magnetic polarity, which pole is where within the sun is flipping. And then you're back at solar minimum again, and there are no sunspots when the sun is organized. And this takes 11 years. So 5.5 years roughly to go from the lowest to the minimum. What usually actually happens is that I think there's a rapid run up to the maximum and a more gradual decline to minimum. But we don't need to worry about that. Something similar happens on Earth every few thousand years. Right now we're in a situation where we're like this. Actually, the northern magnetic pole of the sun, or I should say the magnetic pole that is at the Earth's north pole, north geographic pole, is actually a south magnetic pole. And then over time, that will eventually flip. There'll be a field reversal, and then there will be a north magnetic pole at the Earth's geographic north pole. And we've seen this in the geographic record at Earth, that in cooled magma, there are polarity reversals where the magnetic field in magnetized grains inside the rocks flips direction. It might actually be happening now. The pole migrates a few meters every year, and lately we've noticed that the rate of migration has increased. So the pole might be might be changing. Yeah, and so that's the So the sunspot cycle from minimum to minimum is 11 years, but this is only half a magnetic cycle. I started N down, then I go to N up in 11 years. In order to get N down, I have to go another 11 years. So a magnetic cycle is 22 years, even though a sunspot cycle is 11 years. So there are a few ideas about how these pole reversals work, but one of the oldest is an idea from something called differential rotation, and then something people call the alpha effect. This is a Greek letter alpha, this is a Greek letter omega. And it's related to what we would call the Coriolis force here, when there's a convection twists things in a certain way. So here's the omega effect. It turns out the sun rotates differentially. The equator rotates faster than the poles. And that's true of any rigid object. If you compute the rotation rate at the kind of the mid or the equator of the object as it's rotating, in miles per hour it'll go faster, or in meters per second or something, it'll go faster because it's farther from the rotation axis. But in the sun, it's actually it's actually different than that. It's not just in meters per second it goes faster. It actually goes faster in degrees per second or degrees per day or something. So the equator of the sun takes I think it's about 23 or 24 days to rotate, but as you get toward the poles, it gets up to 25 or 27 days to rotate. So that has the property of taking something that was originally like along a line of longitude and causes it to wrap around to get distended. It's no longer a straight longitude. It gets wrapped around. That's what's shown here with this cartoon. It stretches, in this cartoon, it stretches magnetic fields out and wraps them around. and then these might rise through the surface and make sunspots. That's what's going on here. But if there's a handedness to the convection inside the sun, to the flows inside the sun, so that rising things in one hemisphere rotate one way, say, I got to think about it. I think it would be counterclockwise in the northern hemisphere, and rising things in the southern hemisphere would rotate counterclockwise. No, did I get that backwards? Let's see. Yeah, no, that's right. Counterclockwise. They will be twisted in different senses in the different hemispheres, and that will have the property of kind of reversing what I would call the poloidal field, the pole-to-pole field, with time. And so this is an old idea. This was first proposed in sort of the 1950s or 60s, and I just borrowed this cartoon from somebody in 2013. This BL mechanism is for Babcock and Leighton, and they were doing this in the 50s, late 50s, making similar cartoons. Not as nice as this one. Yeah, there we go. And then more recently there have been different models proposed, but this is just a basic idea. And a lot of models, even if they have other bells and whistles and stuff, basically come back to this idea that there is shearing from differential rotation, then you need to do something with twist. So something that manufactures a magnetic field is called a dynamo, and we sometimes use them on Earth for when we need to make magnetic fields, but there are also dynamos in other stars and probably around black holes and neutron stars. And so here's one question though: are these flows that I showed, are they primarily turbulent or primarily ordered? A long time ago, people thought they were very turbulent, and the turbulence just had some systematic properties. Like in the northern hemisphere, it tended to twist one way, and in the southern hemisphere, it tended to twist the other. So they were essentially turbulent, but had some systematic properties. Or now we've started to think, and I think this theory is kind of more widely believed, is that the flows they're actually sort of large-scale background flows that are very ordered, but then there's some turbulence superimposed upon them that that gives us some scatter in the directions and stuff of active regions. Another question is, are sort of sunspots created all the time, or is flux recycled? Does existing field, as it gets dispersed over the surface of the sun, does it then get kind of submerged and reconcentrated before emerging again? So that would be kind of recycling. Or does the field just kind of completely dissipate, and then you've got to regenerate it all from scratch? And then there's one more thing that's kind of an open question in the field. You know, I'm not finding answers for these or giving you answers for these things. I'm just kind of laying out what we're working on as people who study the sun. Is what causes solar flares and coronal mass ejections. I should talk a little bit about what a flare is. We basically think of a flare as any transient increase in radiation from the sun. So these are X-ray monitors showing bursts in time, where something kind of, there's a burst and then it tapers, a burst and then it tapers. So those are all flares, and you can play some games with. You can say, well, in order to be a flare, you have to have some threshold that's exceeded, because you see all these tiny little fluctuations, and people have actually come up with names for these. They call some of them micro flares or nano flares. And one idea is that there's kind of nano flares going on all the time, and that's what heats the corona. But here's a good movie of a flare, and let me guess, because I changed my password, it's probably going to ask me to do this grant access stuff, but I just do that, and okay. So here are two sunspots. There's the dark regions, and you can see the penumbras around them. And then there are these brightenings between them. So this was taken in a particular wavelength, calcium-2. And the movie here, you can see this is in, let me move my cursor out of the way. You can see that that's in, it's over about 4 hours. No flare, no flare, no flare, no flare. Oh, some brightenings. There the flare starts at about 2:30 and runs for about an hour and a half. And I have this thing about here, comment down here, note the two ribbon structure. There's one southern ribbon and then there's one northern ribbon, and these kind of propagate up. That's a key part of big flares. We don't often see those. Oh yeah, and this movie also needs permission. Sorry about that. So here's another movie, and this is showing something actually getting ejected out into space. It's not just a flare, it's an eruption. And so they call this a coronal mass ejection. This dark thing right here gets launched out into space. And then afterwards, you can see these little bright loops that arch from one side to the other. They call those post-flare loops because the flare is that little thing right there, that little brightening thing that raced along the surface. That's the emission that corresponds to the X-rays. And then as that happens, there are these little flare ribbons kind of move away from the site of the ejection. This is as before. We showed another image like this, an extreme ultraviolet movie, and it shows hot gas or plasma that's at about 1.5 million degrees. And so we have a kind of a standard model for what's going on with a flare, is that there's something called magnetic reconnection here, where magnetic fields that go up on one side and down on the other are spliced, and the ups join the downs to kind of make these new arched field lines that go down, and then the ups join the downs here, or I should say the downs join the ups, and they make kind of, so this makes an inverse U-shaped line, this makes a U line that creates a twisted structure that leaves the sun. And these are all different researchers who found different parts of this model. Here's another pretty picture of a solar flare. And this one's really slow, and this gives you, I like to show this because it gives you an idea of how things actually work on the sun. Most of the time, not much is going on. You can kind of see a little twinkling over here, but not much is happening. So most of the time you see the sun, you see little things, and you think, oh, that could be interesting, but maybe it's nothing. Oh, now something's happening. You see this little dark structure there is starting to lift up. And even this is vastly accelerated. And there's a flare going on. You see that flickering was the detector was kind of saturated. And you don't usually see what's about to happen next. Those dark structures sometimes you see, but you don't usually see them brightening as they rain on down to the sun. So this was a rare event, but it's really beautiful to watch. Well, that's most of the sexy stuff there, so maybe I'll go on from that slide. We're only halfway through it. But and as I had said before, that our society can be affected by these kinds of solar events. So I want to talk a little bit about these kind of space weather things. There are some satellites we put out in space to look at the sun from different points of view. One was called Stereo, and there was a satellite that went ahead of Earth, and it had a left of Earth view. And then there was one that went behind Earth in the Earth's orbit, and it had a right of Earth view. And so then at Earth, we have something that can block the disk of the sun. And so when something is ejected by the sun, like that CME we saw, you see something coming at you, and we call it a halo CME because there's a bright ring around the sun as gas from that object comes toward us. Now, the direction of the Earth, you can see in these side views, is kind of straight up, but this little thing is heading a little south of us, and here you can see this thing heading south. But this CME was headed in the direction of Earth, and so, as I said, you saw that brightening here. We called it a halo CME. These things that take images of the area around the sun but block out the sun are called coronagraphs, because we're looking at the faint emission from the sun's corona. We're not looking at the sun itself. So when these ejections come toward Earth, they can cause problems here, and this mostly comes from CMEs, usually not flares. Flares can cause problems at Earth, but they're usually relatively minor. So we can get some northern lights. That image was taken in Norway. As you can see, we can get damage to satellites. I don't have an image with that. We can get damage to radio communication so that radio pilots can't communicate with radio towers. And flight crews can actually get pretty heavy doses of radiation. So in order to protect flight crews, they divert the flights to lower altitudes, and then they have them fly away from the poles. So if you were on a flight over to Japan from the continental United States, you'd actually go to pretty high latitudes, or to Russia or something. You'd kind of go over the poles. But instead, they'll send the flights to lower latitudes, so they'll have a longer flight path, which requires more fuel, and they'll have a longer flight time, which can throw off schedules. So airlines like to know about solar activity that'll impact the Earth. So there are all these sorts of space weather customers. And you can have power grid fluctuations. And this is an example of a transformer and a power substation that was damaged from excessive currents fluctuating due to a magnetic disturbance. So these are all different kinds of space weather impacts. And again, it's the magnetic fields that do all these things. We can look at here's a CME. We can look at the amount of energy it takes to have a CME. We can look at the the kind of energy stored in gravity or in stored heat, and not much energy stored in gravity. But in order to have a CME, we need to have a lot of energy, and erg is a measure of energy. And really, the only thing that has the right energy density in the corona is the magnetic field. So it's got to be the magnetic field that's responsible for these things. And people had a lot of ideas about how these things started. This was an old picture from 40 years ago now, where if you had some a new sunspot emerged and there was an existing sunspot magnetic field, they would interact, and you could get some places where oppositely directed magnetic fields were, you could get reconnection. But we don't know what the exact trigger of these things are, but we do know a few things. We think the energy is stored in the corona, so people have to talk about a storage and release model, where the energy is stored there, and then it's kind of suddenly released. And this actually, as I might talk about in a minute, is very similar to how earthquakes work. We think there's stored energy in deformed tectonic plates that is suddenly released when the plates shift and slide along each other, and that's what an earthquake is. Well, there's probably something similar there. In the case of the sun, we don't know how long energy is typically stored. We think the corona can store energy for about 24 hours after you dump a bunch of new energy into it, but energy could be stored for longer. And we also don't know what the proximate cause. We know that magnetic fields and the release of magnetic energy are the ultimate cause of flares and CMEs, but we don't know why it's released at a particular time or a particular place. We have this idea, though, that the flows at the sun's surface shift the magnetic field in the corona around by moving the foot points of coronal magnetic fields. And so that itself has the equations that govern the corona's magnetic fields are nonlinear, and then the sun's velocities are convective, and that's a nonlinear process. So whenever things are nonlinear, those kind of systems yield chaotic behavior, like mathematical chaos. So it's not too surprising that this is hard to figure out. So this is going back to what I talked about, these three open questions about solar activity. This is the coronal heating problem is the first one. And we think that convection is important here, and there are these velocities that push magnetic fields around and create electric current, but we don't know exactly how the currents are created or dissipated. For sunspots and why they come and go, well, we think there's some kind of dynamo going that's on large scales based on the large scale patterns of magnetic fields, but we don't yet know whether it's mostly turbulent with some ordered properties or it's mostly ordered with a bit of turbulence superimposed. And then we don't really yet understand what causes solar flares and coronal mass ejections. We know they're magnetically driven. We probably think that flows at the photosphere can cause the coronal magnetic field to become unstable. And then magnetic reconnection, which we're still trying to understand and which we study in experiments here on Earth, and there are experiments going on at UW and Madison and stuff, for instance. But I still characterize it as mysterious. There's a lot we don't know about it. Enables the field to release some of this stored energy and relax to a more stable state. But a key thing is that basically these kind of surface motions act on magnetic fields that are anchored at the surface and extend up into the corona, and input energy and that energy is released. That's a kind of a common theme. And then the recap of the main ideas that I had in one of my introductory slides was that, well, the sun is an active star and it has things like sunspots, and we now know there are active regions all around those. And I didn't talk much about filaments and prominences, but there are things that extend up above the solar surface. We did talk about solar flares and coronal mass ejections, but all of these are manifestations of solar activity, and they are driven by the sun's magnetic field. So if the sun didn't have a magnetic field, it would actually be a pretty boring place. And then these magnetic fields sure make the sun fun to study, both from just a intellectual curiosity point of view. How does the universe work? And then it's fun to watch things go boom on movies and videos and stuff like that. But also there are these space weather consequences to solar activity that motivate. There are practical considerations that motivate us trying to understand solar activity. I think that's about all I prepared. Oh, I should tell you guys about this. They're building a big telescope on Hawaii, the Daniel K. Inouye Solar Telescope. DKI was a long-time senator from Hawaii. He's known there by those initials, much as we know JFK or FDR by their initials here on the mainland. So it's on Maui. It sits atop the Haleakala, which is there's a national park there, or at least a monument there. You might have been fortunate enough to do some hiking there. And so it's pretty high up, and the reason they go high up is it gets us above most of the moisture in the atmosphere, which is good for infrared observations, for seeing magnetic fields better. And I think I just told you guys that. And here's a picture of the telescope. We've just had flight back in February. They're still commissioning it. I put in some proposals to use it for observations, but it's got a big primary mirror, the big hole where the sun will come in, about 4 meters across. And then there's a secondary mirror that gathers the light that you want to use for your science, and but blocks most of the heat that you don't. And so there's something here they call a heat stop, and then the light beam goes down in the interior, down here to what they call the Coude level, and there's a lot of instruments there. That's where the science is done, and this is a big turntable that moves, so the instruments move as the upper housing moves to follow the sun. And then the current solar telescope in Big Bear, California, 1.6 meters in aperture. So this is a larger aperture, gives us higher spatial resolution. And this is for who are telescope geeks. You can change the altitude and sort of how high in the sky the telescope is pointing at, which latitude, and then its azimuth, where along the sky it's pointing, left to right, basically. And then there's a particular configuration which allowed that heat dump. And then there's an off-axis design. Unlike most other telescopes, there are no elements, no struts or wires or anything in front of the primary mirror, and that's because if the sun did shine on it, it would produce a lot of scattered light and stuff. And I don't think I need to tell. I could say this, that if we did have support struts for what we call the secondary mirror, it would produce these kind of diffraction patterns you've maybe seen on pictures of other stars. And that's just an image that shows how big DKIST is. So I should really probably stop there. Here's a movie of granulation with DKI. And yeah, I don't think I have anything else. So, oh yeah, there's that. And did I say that? Yeah, but I'm going to go back to this just because it's fun. So I'm going to go into the chat window. I don't know if people can activate their chat windows. If you joined and you haven't done anything with your, there you might see at your right, there's a couple little purple arrows. You can click that out. And if you click on this little bubble over here on the left, that should give you stuff to chat about. So I could chat, does anyone have any questions? And then I can also scroll, drag out, and show you, you could probably unmute your audio if you wanted. You don't have to. So I'm going to scroll that back. What made you decide to study, I guess I'm going to say study the sun? I was interested in nuclear fusion, but when I went to grad school to get my PhD, federal funding for fusion, had been cut. So I studied another place where fusion happens. If we could get fusion, we could get fusion working on Earth. We'd be able to kind of stop using fossil fuels and would have much less radioactive waste or risk of meltdown compared to nuclear fission, which is the current form of nuclear power. But I also found magnetic fields very interesting. And the sun certainly has some interesting magnetic fields. And now that I think about it, I've probably been studying the sun for over 25 years now. So, are there questions for anyone? I don't mean to detain people. I've already spoken for quite a while. So if anybody wants to depart, they can sign off, and I won't be offended. I should teach you how to sign off. You know, you can always X out your system, but if you click on this little circle on the left, you'll get then here's a little leave session button. I think you can also, I think there's an option up here to, oh, maybe not. Oh yeah, down here you can leave it, says leave a session down at the bottom. Other questions? I do have one favor, please. Yeah. Let me erase this. I recorded. I could upload it to YouTube or something like that. On YouTube and send Jessica the link. Let Jessica know, and I do have one for. Let Jessica know if the video or audio were glitchy for you. Then I'll ask her tell me. On my end, I usually don't know if it's bad for viewers, but I am curious how good it is.
Can I reply audio?
Yeah, I can hear you. Yeah.
This is Donna. The audio and the visual were great.
Oh, good, good.
Fascinating subject. Thank you.
You're very welcome. Okay. Okay, I'm going to go ahead and sign off then. Thank you all for joining, everyone.
Thank you so much, Brian. We appreciate your time.
Yeah, you're welcome, Jessica. Enjoy the nice weather, everyone.
You too.